Okay? So we have this network attached storage philosophy that we were using, but the speeds were still relatively slow. Okay? So Fibre Channel came around in a time where we were running 10100 on the local area network, and Fibre Channel kind of came blazing in at about 1, 2, or 4 gigabits per second. Okay? So in all actuality, storage area networking using the Fibre Channel protocol, okay, was actually blazing fast. All right? So what we had is this new kind of NIC was given to servers and disks, all right? And this was actually a Fibre Channel host bus adapter, okay? This connected off to kind of a back-end storage area network, okay? Where we maybe had servers that access data on disks, all right? But this back-end Fibre Channel, guys, allowed us to do block-level storage at much, much faster speeds than we can provide on the local area networks at that time. Okay? We got much more efficient use of the bandwidth for our storage area networks than we did on our local area network side. All right? So that is kind of how we evolved from where we had that direct attached storage to network attached storage to finally storage area networks, okay? Which is where we're at today in a lot of what I had been seeing traditionally through consulting is that even medium-sized businesses, okay, not necessarily small business, but from medium up through enterprise, more and more are employing the use of dedicated storage area networks within their data centers, okay? So Fibre Channel was really introduced to address kind of those speed concerns, right? And we also got the added benefit that we were using block level storage so we could use boot from SAN, okay? Meaning we didn't have to have any local disks on our storage. We could completely and utterly rely on boot from SAN methodology, all right? Now, what I want you guys to understand from this point forward in all of our discussions throughout today is that when we talk about storage area networking, whether we're talking about Fibre Channel protocol, whether we're talking about Fibre Channel over Ethernet, whether we're talking about FCIP or Fibre Channel over IP, whether we're talking about iSCuzzy or ISLB, okay? We are always going to be transporting the same payload, okay? What is that payload, guys? What payload am I talking about? Scuzzy, right? We're always going to be transporting Scuzzy. Okay? I pulled up a nice chart off the internet today. I've been finding myself using it more and more for my students. But I want you guys to see what I didn't create this, someone else created it. The many faces of Scuzzy, as they say. Okay? So when we look at this, I think it gives an awesome representation of whether we're using Scuzzy, native Scuzzy, whether we're using iSCuzzy, Fibre Channel, or FCOE. Look what's always at the bottom of that stack, guys. The Scuzzy command sets, okay? No matter whether we're encapsulating that in Ethernet, okay? Whether we're encapsulating that in Fibre Channel. As we go up through our representative stacks, no matter what protocol we're using, we're always going to end up transporting Scuzzy read-writes, okay? So we're always trying to read or write through some storage means, but in the end, it's always Scuzzy, guys, okay? Notice here, just native Scuzzy goes from a parallel Scuzzy to SPI, Scuzzy, 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 okay? We move over to FCOE, okay? We're going to encapsulate that in Ethernet, all right? Then once we get past the Ethernet MAC phase, or layer 2 of what we're going to call FCOE, we're just going to start encapsulating the Fibre Channel stack, okay? And Fibre Channel ends up in Scuzzy, okay? So you're going to see the same thing in Fibre Channel, except the first 2 layers between Fibre Channel and FCOE, we're just replacing those first two Fibre Channel layers with the dedicated Ethernet layers, okay? But no matter what we do, we always end up at the same thing, okay? Don't forget that, guys. That's important, okay? So as we start encapsulating all of these Scuzzies through these different kind of methodologies, whether we're encapsulating in Ethernet, whether we're doing TCP/IP in Ethernet, okay? We're going to be adding overhead as we do that. So we're starting off with Fibre Channel, so we're going to start off with really the base MTU that we're going to be dealing with from the get-go, okay? What we have within our headers, okay, with Fibre Channel Protocol, we're back to Fibre Channel Protocol, okay? When we do Fibre Channel Protocol, we are going to have a maximum MTU of 2148 bytes, okay? Now, 2112 bytes, that is our maximum Scuzzy payload. Okay? So everything between that, so 36 bytes is the added Fibre Channel header. Okay? So our actual Scuzzy payload will never exceed 2112. Now, what a lot of people don't know about Fibre Channel is that we actually transmit it in what we call Fibre Channel words. Okay? Now, each Fibre Channel word equals 4 bytes. Okay? So each Fibre Channel word equals 4 bytes. We can transmit up to 537 words in a full frame. Okay? Now if we do the math there, if I pull up my handy dandy calculator. Alright? And if we do the math, if we come in here and say 537 times 4, we get 2148. Okay? So that is where we get our max payload for Fibre Channel frames. Or sorry, our max MTU for Fibre Channel frames. Okay? So again, we have 4 bytes per word and up to 537 words in a full Fibre Channel frame. That's how many we can transmit. Okay? So that's where the math comes in. That's how we end up with 2148. Okay? Now, there's a couple key fields inside the Fibre Channel header. Of course, we're going to have a source, we're going to have a destination, we're going to talk about those in a minute. The one I want you guys to know is what we call the OXID. Okay? So it's called, the full name is actually called the Exchange ID. Okay? What the Exchange ID is going to do is kind of allow us to, I equivocate it to a TCP flow. We're identifying a certain flow of information. Okay? Like TCP, guys, any given flow is always going to follow the same path. Okay? So if we have many paths in our storage area network between a source and a destination, anything with the same OXID, guys, is always going to follow the same path. Okay? Because that is a single flow within the Fibre Channel realm. Okay? So just know that OXID is identifying a Fibre Channel flow. All right? We're going to see this pop back up when we start talking about load balancing within a storage area network. Okay? Now, with all that said, that's kind of all just fluff, right? It's just all the boring bits. So let's get to the real meat and potatoes of Fibre Channel or storage area networking. Okay? I want to talk about how we differ between what we're used to on the campus or LAN or data center side, just traditional Ethernet-based networking, versus Fibre Channel networking, versus storage area networking using the Fibre Channel protocol. All right? I want to start at the physical layer. Okay? Physical layer, guys, we're talking about, we're going to use the same kind of fiber optic cable. That hasn't changed. We can use the same fiber optic LC to LC, both on the Ethernet side and the Fibre Channel side. Okay? What does change at kind of the physical layer is the SFPs. Okay? A lot of people think, well, we can just use these SFPs, right? No. Fibre Channel has its own SFPs. So we're going to need to replace or use the proper SFPs for Fibre Channel communications. All right? What we typically see is these are going to operate at 1, 2, 4, 8, or 16 gigabits per second. Okay? Again, the speed is going to be dictated by the speed of your switch. Okay? So always check with your switch manufacturer before you go buy some SFPs, because you may have one that only supports 2 gig, and you definitely don't want to go spend the money buying 16 gig Fibre Channel SFPs if your switch only supports 2. Okay? So the real difference at the actual physical layer, guys, are these small form pluggable transceivers that we're going to be inserting into these switches. Okay? You'll see on our 5Ks, we have all the same, most of them are 10 gig or 1 gig transceivers on the Ethernet side. When we get over to the Fibre Channel side, we're going to see mainly 4 gigabit per second Fibre Channel transceivers. Okay? So different transceivers. We move up to layer 2, guys. When we talk about layer 2 addressing on Ethernet networks, what kind of addresses are we talking about here? Little interaction, guys. What kind of addresses do we have at the Ethernet? Right? MAC. We have MAC addresses. Specifically, 48-bit MAC addresses, right? So these MAC addresses are unique at layer 2 within the network, based on usually the OUI within that MAC address, right? Guaranteed to be unique, I should say. Within the Fibre Channel realm, we have very similar addressing, okay? Except at Fibre Channel, we're going to have what we call 64-bit worldwide names, or WWNs for short, okay? So at Fibre Channel, I want you guys to be very familiar with 4 different types of worldwide names, okay? There's a lot of worldwide names. I want you guys to be familiar with 4, okay? I'm not asking much, all right? So let's dive these out. The first one we're going to talk about is actually called the worldwide node name, okay? Or we can call it the node worldwide name. Thank you, Cisco, right? All right? So those are synonymous with each other, okay? Every node on a Fibre Channel network is going to have one of these names, all right? So I'm just going to type this out. Every node has one, okay? The next one I want you guys to know about is what we call the worldwide port name, okay? Or the port worldwide name. Thank you, Cisco, right? Every Fibre Channel HBA, okay? So every host bus adapter that we have is going to have one or more worldwide port names, okay? Depending again on how many ports it has. So every host bus adapter has, one or more, okay? Every port on that host bus adapter will have a worldwide port name, okay? The next one is actually called a worldwide switch name, okay? Or switch worldwide name. Thank you, Cisco. Okay? Every switch on a Fibre Channel network will have a worldwide switch name. Okay? Every MDS switch, because we're talking about MDS. I'm not talking about Brocade. I don't care. We're studying for the Cisco Certified Internetworking Expert Data Center exam, right? So every switch will have one. Okay? The key here is, guys, later we're going to start talking about vSANs, or virtual storage area networks. When we start talking about vSANs, every vSAN is also going to have a switch worldwide name, okay? So for now, let's just learn that every switch is going to have one, okay? Every switch is going to have one base worldwide switch name. Just like every switch has a base MAC address, every switch will have a base worldwide switch name. All the vSANs are just going to derive their switch worldwide names from the base switch worldwide name, okay? So for now, just know that every switch has at least one, okay? The last one I want you guys to be cognizant of is what we call the worldwide fabric name, okay? Or the FWWN, thank you, Cisco, okay? Now, I guess if we're saying MDS switches, okay, every MDS switch port will have a worldwide fabric name, okay? So every switch port has one. I'm going to show you guys 2 different ways to find the worldwide fabric name for a specific port, okay? It's actually real simple. If you just say show int Fibre Channel 11, for example, what you're going to see in that output under there is it's going to say port worldwide name, and it's going to give you the worldwide name. What I hate about that is it says port worldwide name instead of fabric worldwide name. So a lot of people get that confused with the PWWN. That's not what it's referring to. When you do a show interface Fibre Channel and it says port worldwide name, that's actually the fabric worldwide name. Okay? Now, just so you guys aren't shocked and awed when you go in and see these addresses, if you've never seen them before, they're going to look something like this, and I'm just going to use basic numbers for kind of brevity's sake, but we're going to see something that looks like 00, 11, 22, 33, 44, 55, 66, 77. Okay, so we're going to have 1, 2, 3, 4, 5, 6, 7, 8 fields each 8 fields represent 8 bits. 8 times 8 is 64, right? Okay, so that's what it's going to look like. They're very long. They're not very nice to try to remember. Okay, so we're going to have some ways that we can kind of make that easier, more human readable throughout this study. Okay, so those are the 4 main types of names or worldwide names that I want you guys to be familiar with basically throughout your studies. These are going to be the big ones. Okay, now as we move on down, as we start talking about layer 3, what kind of addressing do we have at layer 3, guys? IP addressing, right? So we have IP addressing, and those are usually 32 bits in length if we're talking about IPv4. Okay? When we start talking about Fibre Channel, okay, we are also going to have something called the Fibre Channel ID. Okay? And the Fibre Channel ID is a 3-byte field. Okay? So it's a 3-byte field. It's going to be represented in hexadecimal. Okay? So what we're going to see is something that looks like this. 0x, and we're going to have 2 spaces. Okay? We're going to separate 2 spaces. I'm just drawing lines so that you guys can see. I'm going to have a clear delineation between these bytes. Okay? That is also why I refer to this in bytes rather than bits. Okay? Where we have 32-bit addresses at IP, we have 24-bit addresses with FCIDs. But I like to, again, refer to them as bytes because it's separated. This address is separated into 3 distinct fields. Okay? This first field, or these first 8 bits, are going to be what we call the domain ID. Okay? Every switch in the Fibre Channel network is going to have a domain ID. Okay? As they address their clients, whether those clients are initiators or targets, okay, this first 8 bits here is going to be represented with that switch's domain ID. Okay? The second field here is going to be the area ID. Okay? So the second set of 8 bits is going to be the area ID. Normally, every switch port on an MDS switch will have its own area. So it'll get a full area. All right. Now that's normally. You will see some cases where an area may be shared. Okay, where it may be common between multiple ports, but I've never seen it like that. I've always seen every switch port has its own dedicated area. All right. This final field is going to be dynamically assigned to the host, whether again that's an initiator or target. But this is dynamic. Okay, so the last 8 bits is actually going to be the addressing of that initiator or that target. Okay, so we have kind of these different addressing schemes that we have to get used to already, guys. Now instead of MAC addresses, we're dealing with worldwide names. Instead of IP addresses, we're going to be dealing with things like Fibre Channel IDs. What I really want you guys to get familiar with is this concept that we have these reserved bytes within a Fibre Channel ID. Okay, very important, guys. Get this down early in your studies, as it will help you as you progress through your studies. Trust me, what we're talking about here is core knowledge within storage area networking. Okay, truly go in and try to understand this stuff first. It will make when you go in and start configuring these switches a lot easier. I promise you. Okay. So I want to move on and give a little background just around Fibre Channel networking in general. I want to diagram a lot of this out when we start talking about port types, about principal switches. But I first want to let you guys know, before we get to that diagram, what this FCF acronym is. This stands for Fibre Channel Forwarder. Okay? A Fibre Channel Forwarder is a Fibre Channel switch on the network that is actively participating in the fabric. Okay? By actively participating, I mean he is going to be a smart switch. Okay? He is not a dumb switch that's just going to forward based on a MAC table, guys. These Fibre Channel switches actually participate in a routing protocol called Fabric Shortest Path First. Okay? Again, Fabric Shortest Path First is based on OSPF, except it's been adapted for Fibre Channel networks. It uses the same Dijkstra algorithm and everything. Okay, we're going to have shortest path database, we're going to have routes, all of that. Luckily for us, it's automatically configured behind the scenes in a Fibre Channel network. But these switches, guys, this is the key. These MDS switches are participating in routing. okay? They are also participating in DHCP, okay? These local switches, these fiber channel forwarders, will be handing out FCIDs to their directly attached clients, okay? So they will hand out FCIDs to their targets and initiators that are directly connected to them, okay? So a fiber channel forwarder, guys, is not by any stretch of the imagination a dumb switch, okay? It is a smart switch that participates in routing and both a pseudo kind of DHCP relationship with initiators and targets, okay? Now I want to cruise over here to my diagram, and I want to talk about a regular fiber channel network, guys. So while we're waiting on Zane, you guys probably saw I went ahead and kind of drew out a network here. Okay, so a traditional fiber channel network is going to have different sets of switches within the network. And what we're going to see, there's a couple different SAN designs, but the one I'm depicting here within storage area networking, we call an edge core edge design. Okay, believe it or not, we have like a collapsed core storage area networking topology. We have an edge core design storage area networking topology. What I'm depicting here is just the typical edge core edge. It's what you're going to see in a lot of different deployments where you have these edge switches where our different initiators and our targets actually connect to. Okay, the core is just there to aggregate all of the edge switches together. All right, so within this, as I mentioned, a disk or a shelf of disk, you guys are probably used to like EMC and NetApp. These are going to be what we refer to as fiber channel targets. Okay, so the disk is actually the target, and the disk knows it's the target. Okay, there's some special fields that it uses to register with what we're going to learn as the fiber channel name server, and it's going to register itself as a target within the network. Likewise, these servers are going to be referred to as initiators, okay? I'm just going to say init for short. So we have what we call targets and initiators within the fiber channel realm. The initiators are always going to initiate the communications with the targets, okay? That's always going to be the case. Initiator and target relationships, all right? Now, within this storage area networking, or the storage area network, you guys need to get used to some new port types, okay? You know how in traditional Ethernet switching we say stuff like switch mode access, switch mode trunk, okay? It's changed. We have different port types within a storage area network. The first one I want you guys to be aware of is this relationship between the edge switch and the server, okay? From an edge switch's perspective, when it attaches to an initiator or target, that is always going to be what we refer to as a F port or a fabric port, okay? So when we actually go into that port and configure it, we're going to say switch mode F, all right? From a server or the initiator or target's perspective, that is always going to be an N port or a node port. Again, we don't have to configure that. They already know they are an N port, okay? So throughout this whole topology, we can kind of fill in these blanks. N, F, F, N, N, F, okay? Those are all either fabric or node ports. And what we're going to see is there's always, 99% of the cases, I'm going to explain that one off here in a little while, 99% of the time an F port is always going to connect to an N port, okay? We're always going to have that relationship. All right. Now, when we connect switches together, guys, when we connect two fiber channel forwarders together, what would that be if we were just doing Ethernet-based networking with VLANs? What would these links be in between here? Trunks, right? Good job, Tim. Those would be what we consider trunks, or in the Nexus world, .1Q trunks. Likewise, within storage area networking, these are going to be what we call E-ports or expansion ports, okay? Think of it like this. We're expanding the fabric, okay? So these would all be what we refer to as E-ports. Okay? Or expansion ports. Again, we're expanding the fabric. Guys, this E-port designation, as we're going to see here in just a second, plays a very special role in setting up the fabric. All right? And speaking of fabric, when we look at this topology, okay, because this is a typical storage area network, all right, what we tend to see is that storage area networking admins or engineers like to take this fabric and split it right down the middle. Okay? We're going to create kind of an illusion of what we call SAN islands. Okay? This will become SAN A. This will become SAN B. Okay? So we have two disparate fabrics. We kind of have a fabric A over here, and we kind of have a fabric B over here. All right? What this does, what the initial design was that we created, say, this fabric on this side, SAN B. And what happens is we go to make a change over here, and we kill the traffic flow, okay? We maybe have to do an upgrade. So they were like, let's create an exact replica of this SAN and copy it over here. We'll create this concept of SAN islands, okay? So what they've done is they've isolated fault domains, okay? Because now I can come in here and I can operate on this switch. You know, I can modify some fabric parameters. I could do a switch upgrade. And when this guy was originally using this path, once that failure is detected and he no longer has communications to his target through SAN B, he's just going to start using SAN A. Okay? So we have the ability with this islanding technique, that's not even a word, I just made that up. With this island technique, we have the ability now to come in and make modifications to one side of the fabric, okay? And we can still have this other side available as a path for us, because the I/O drivers for Fibre Channel are inherently multipathing, guys. It is going to be cognizant. Whatever servers driving these Fibre Channel HBAs in this server are going to be aware of the two paths to the destination, okay? Now, when it detects that it can no longer reach the destination through SAN B because maybe we're doing a reboot on this switch, it's going to just be using SAN A. Okay? So that is why they created this SAN island technique. But notice, we had to mimic the entire physical topology from SAN A to SAN B, meaning we have to have 6 different switches in place for this to happen. But that's why they did it, guys. We have 2 disparate, completely physically separate fabrics to run on. Okay? We have SAN A and SAN B. So I want to talk about what happens when we actually crank up these E ports here. Okay? Because when we turn on these E ports, when we say switch mode E and actually bring that link up, some things happen in the background that us as engineers, unless we study it and research it, are not even cognizant of. Okay? So I want to talk about those. We're going to have what we call the switch internal link service run. Okay? This is again the switch internal link service. Okay? This has a set of steps that it goes through when we bring up these E-ports. Okay? The first one is going to be, the first step I should say, is exchange link parameters, okay? Or ELP for short. What ELP does, guys, is it helps us first resolve what we call buffer-to-buffer credits, okay? So locally on each link, to ensure a lossless fabric, all right, we're going to exchange what we call buffer-to-buffer credits. Buffer-to-buffer credits are basically how many frames can we send out on the wire, okay, before we receive an acknowledgement back, before we have to stop transmitting. So we have a finite number of buffers. Don't worry about it at this point. That's going to be my last slide of this presentation. We're going to talk all about buffer-to-buffer credits. But during this first step, this ELP, exchange link parameters, we're going to tell the other side how many received buffer-to-buffer credits we have. Okay? We're also going to send out some timers. Okay? So what are our specific timers for Fibre Channel? We're going to exchange those during this step. After that is complete, we're going to move down to this ESC, or exchange switch capabilities. Okay? Here we're going to exchange some FSPF parameters. Okay? And there's also a special field in here that's going to allow us to identify whether we're a certain vendor. Okay? So the MDS switches actually have a special designation. I think it's an 8-byte field, or yeah, it's 8 bytes, that allows us to identify whether we're an MDS switch. Okay, so if we have 2 MDS switches, a special thing happens. Okay, we get down to this exchange peer parameter steps, and we're going to exchange what vSANs, or virtual storage area networks, that we have. Okay, you're going to see why this is important, guys. When we get on 2 different switches and we start exploring vSANs, okay, they're able to tell whether or not they need to transmit a certain vSAN over a trunk or not. Okay, they are aware of what the other switch has in its vSAN database. Okay, very cool stuff. Once that step is complete, again, this is a Cisco proprietary kind of step. This is where we're exchanging Cisco stuff, vSANs, our Cisco invention if you didn't know. After we complete this step, we're going to move down to exchange fabric parameters. Okay, so this is where we're going to have something called the principal switch election. Okay, so we're going to have to exchange priorities. All right, so we're going to elect what we call the principal switch on the network. Okay, so let's go back to the drawing and kind of hash this out. So when we bring up these e-ports, guys, every switch on the network is going to have a default priority. Okay, so every switch on that fabric is going to have a default priority of 128. Okay, that's how we start out. Again, we're dealing with more of a layer 2-ish technology here, so a lower priority is actually going to be better. All right, so what happens by default is all the switches have a priority of 128. Okay, everyone's tied. So what's going to happen is the switch with the lowest switch worldwide name will get elected the principal switch. Okay, so the principal switch is going to be the switch that hands out the domain IDs within the Fibre Channel network. Okay, he's going to be the guy that hands out the domain IDs within the Fibre Channel network. So when we elect a principal switch, or when a switch is elected the principal switch, it's going to lower its runtime value. Whoops. To 2. Okay, so let's say this core switch, just based on his switch worldwide name, was elected the principal switch. He's going to have a configured value of 128, but a running value of 2. Okay, this is a non-preemptive role. Once he's elected principal switch, until the fabric is reinitialized or reset, he is going to be the principal switch forever. Okay, so he lowers his runtime priority down to 2 if he's elected the principal switch, and he starts handing out domain IDs. Okay, so he may hand himself out a domain ID of 1. Okay, he may hand this guy a domain ID of 2, and this guy a domain ID of 3. Okay, this is per fabric, guys. So a completely separate but identical process is happening on the other fabric when we do this. Okay, again, we may come in and we could static the priority. We as the admin could come in and say, I want this core switch on fabric A to have a priority of 1. Okay, so we go in and we can statically set that priority to 1 to guarantee that he will win that election. Okay, so we could set that to 1. These guys are going to default to 128. Okay, and likewise, he is going to hand out domain IDs on this fabric. They could be the exact same domain IDs we're seeing over in SAM B. Okay, or they could be different. It doesn't matter. They're completely separate fabrics, guys. So we could come in, we could assign this guy domain 1. Whoops. Could assign this guy domain 1, this guy domain 2, and this guy domain 3. Okay? It doesn't matter. Separate fabric, the other guys aren't even aware of us. Okay? But the key here is that this principal switch election happens, and then domain IDs are assigned. Okay? So if we go back to the last 2 steps of our internal link service, once we establish that we have a principal switch, we're going to do domain identification. Okay, so we're going to say, hey, the fabric's ready to start assigning domain IDs, and then it's going to request domain IDs. So all the other switches are going to come in and say, oh, I need to request this ID. All right, so that is the switch internal link service. As we do that switch ILS service, our entire fabric is built. Okay, guys? From our domain IDs to our principal switches to our FSPF routing tables. Okay? It's all done during this service. Okay? But I want you guys to have a good view of what happens in the beginning. It took me a long time to realize that this switch ILS thing happened in the background when we configured ePorts, guys. So I want to convey that to you guys early so that you guys are aware it's happening, okay? Because you might see some very cryptic messages that say something like switch ILS ESC failed, okay? So I want you guys to know that that's something happening when you're trying to bring up the fabric on the ePorts, all right? Now, I have to mention that domain IDs, though we hand them out from the principal switch, we could statically assign those. Okay, so if we come back to our diagram here, let's say that our edge switch down here, let's say that we change things up, okay? What actually happens during the switch internal link service when we start doing this domain ID assignment is every switch initially has a domain ID of 0, okay? This domain ID of 0 is what we call a preferred address, okay? So when he comes out and he finds, the principal switch has been elected, he comes out and says, hey, I would prefer to have a domain ID of 0. Okay, 0 is an invalid domain ID. That is what all switches start off with as their preferred address. The principal switch is going to say, yeah, 0 is not a valid ID. How about you take 3? And this switch is going to say, okay, because I was just preferring this address of 0, I will go ahead and use this 3 that you're telling me I can use. Okay? Because when I prefer an address, it means I would prefer to have it, but I'm not going to force it on you. Okay? Now coming back, we also have the ability to do what we call static assignment. Okay? So I could come in here and say, hey, I'm going to say this is my static domain ID. And when I come to the principal switch, I'm going to say, hey, I'm using domain ID 2. I'm using it, you can't stop me, okay? If 2 is already taken somewhere in the network or somewhere already in the fabric, okay, and the principal switch already knows about that, he has the ability at this point to say, hey, you can't have 2, okay? You can't have 2. So since you don't want anything but 2, I'm going to cut you off from the fabric, okay? That is a static assignment. Had this guy come in and said, hey, I would prefer to have 2, then the core switch here, the principal switch, would come back and say, hey, 2's not available, but you can have 5, okay? And then he would take 5. The difference between static and preferred domain ID assignment is that if we prefer it, we'll take whatever the principal switch tells us, whether it's the one we're preferring or another one. If we say we're statically requesting this domain ID and this domain ID specifically, if the principal switch can't allow that domain ID on the fabric, we're going to be separated from the fabric at that point. Okay, so that's the difference between static and preferred domain ID assignment, guys. Again, the safer means is to do a preferred domain assignment. Okay, that is always going to be the safer way to go if you're trying to do static, or I shouldn't say static, if you're trying to manually configure the domain ID. So let's put 2 back up here. Okay, so that is how we kind of go through the domain ID requesting and how we can manually configure it from an administration perspective. We're going to see with some of the security protocols that it's going to be necessary to go in and manually configure these domain IDs. And 99% of the time, if I'm doing this in production, I'm just going to put a preferred address in there rather than a static entry. Okay, so after this has all happened, guys, after all this principal switch has been elected, we have the domain IDs, everything's set up. All of this was accomplished through what we're going to see are called the FC domain commands. Okay, so I'm going to do a demo on those rather than going through each one, the syntax of every FC domain command. I'm going to go through and show you how to modify priorities. I'm going to show you how to modify domain IDs, how we can prefer or static those. I'm going to show you how to create those fabrics. Okay, what I want to talk about next is the process that a lot of the hosts go through, or all the hosts go through, I should say, when we connect them up to the Fibre Channel network. Okay, because we're going to have some communications like floggies and ploggies and PRLIs. Okay, and I want to explain what those do and how those kind of happen. All right, because that's going to dictate how we route within the storage area network. Okay, so let's go back here and let's imagine that this server, again, just for brevity's sake, I'm going to say this server has a worldwide port name of A. Okay, this disk has a WWPN of B. All right, just for brevity's sake. So what's going to happen is when we connect this F port to the network, when we get into that switch and we say switch mode F, put it on whatever fabric it's going to be in, what's going to happen is this guy's going to do what we call a floggy. Okay, so he's going to do a floggy, or what we call a fabric login. Guys, this is done to a well-known multicast, a well-known FCID. Okay, it's actually like 0xFS F, 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 E. Okay, so we're going to do a floggy to that address. So when that floggy hits that directly connected Fibre Channel forwarder, what's going to happen is he's going to have sent his worldwide port name, his worldwide node name, and basically he's going to request that he gets an FCID back. Okay, so this was that DHCP portion, kind of DHCP-ish portion I was talking about earlier. So what's going to happen is this switch is going to register that, worldwide port name A, all right, and he's going to assign back an FCID to that guy. So he's going to say, hey, I'm going to give you an FCID, and maybe that's 0x, okay? And guys, what is his domain ID? 3, right? So those first 8 bits are going to be 03, okay? The next 2 bits are going to be the area. Let's just say the port that this guy's hanging off of is associated with area 00, okay? And maybe the dynamic ID that he gets at this point for this specific worldwide port name is also 00. So that would be his FCID. So this guy is going to build what he calls a floggy database, okay? So this switch builds a local floggy database, okay? So if we did a show floggy database from this switch, we would see this worldwide port name to FCID mapping, okay? Likewise, that same process would happen up here, and we would have worldwide port name B associated with some Fibre Channel ID that would represent the domain ID, right? So this one would be 01, 00, 00. Okay? So we would build that local floggy database on these switches. Okay? The next thing that would happen, guys, is this guy would shoot out to the Fibre Channel name server. Okay? Now, some people wonder or some people question where the Fibre Channel name server is. I've always been taught that the Fibre Channel name server or the FCNS database is where the principal switch resides. Okay? What other theories I've heard around the Fibre Channel name server is that all hosts are going to listen to this, or all Fibre Channel forwarders are going to listen to this well-known address of 0x FFFFFC. Regardless of where it goes, what I want you guys to know is that we are registering ourselves with the Fibre Channel name server database, and this is in the form of a ploggy or a port login. Okay, so we're going to build an FCNS database. Okay, so I'm just going to put FCNS in here. This guy, likewise, is going to do a ploggy to that well-known address of 0xFFFFC. Okay? What's going to happen here is they are going to register their worldwide port name with their FCID to that FCNS database. So within the FCNS database, we're going to have, A is that 030000, and B is 010000. Okay? Now, whether it's replicated by the principal switch or if all switches are just listening to that, what's going to happen is every switch is going to have a copy of this FCNS database. Okay? As it builds, as initiators and targets are added to this network, this FCNS database is going to grow, guys. We're going to have worldwide port names to FCID mappings for every initiator and every target in the network. Okay? So everyone has a copy of the FCNS database. Only the local switches have copies of their local floggy databases. Okay? That's the difference. Everyone sees the FCNS. Floggy databases are local to the switches. Okay? Now, after we've built this, guys, this kind of demystifies or helps us demystify the whole concept of routing within the Fibre Channel network. Okay? Because what's going to happen at this point, okay, if we're on an initiator and we know that we want to talk to this target, okay, we're actually going to do a ploggy up to that target as well to initiate the communications, and then we can start communicating from that initiator to that target, okay? So what happens at this point? How do we know how to reach that target in the network? Well, normally we're going to be zoned with that target. We're going to talk about zoning here in a little bit. But what's going to happen down here is that some admin's going to say, okay, you are looking for worldwide port name B. Okay? So he knows that he's going to be doing reads and writes to this storage system based on his worldwide port name. Okay? Now within the Fibre Channel header, we have destination and source ID fields. Okay? But they are only 3 bytes or 24 bits long. What does that indicate is in that Fibre Channel header? Worldwide port names or Fibre Channel IDs? What do you guys think? If it's only 24 bits long, it can only be one of the two, right? One's 24 bits, one's 64 bits. Okay? So we're going to be talking, even though we're going to be referencing the worldwide port name, okay, we are going to be transmitting using the Fibre Channel IDs. Okay? So what happens is this guy, this server, is going to have a way to kind of do like an ARP. Okay? And they actually call it a FARP or a Fibre Channel ARP. Okay, so he has to find out, or he has to be able to resolve that Fibre Channel ID to worldwide port name, or rather that worldwide port name to Fibre Channel ID. Okay, so again, I've seen 2 different methods for this. I've seen this guy do a Fibre Channel ARP, or I've seen it where the actual initiators and the targets have been programmed to listen to this address. Okay, so that they build the FCNS database inside themselves. Okay, so that they have a local copy. So when they know they have to go to worldwide port name B, they're able to easily resolve that to 010000. Okay, so what happens when he wants to do that communication is he's going to send that Fibre Channel frame out to his local switch. Okay, so if he was wanting to communicate with B, he would initiate that communications and he would send that frame up to this guy. Okay, so he's going to B. What he's going to do, guys, is he's going to say, okay, I am going to 010000. That is not my domain, so I need to look that up in my Fabric Shortest Path First routing table. So he's going to look it up. He's going to see that to reach domain 1, he needs to go out this interface. Okay? So he's going to send that frame, and it's eventually going to get up to the core switch. Okay? The core switch is going to say, okay, I am not domain 1, because he's looking at the Fibre Channel ID. Okay, so he's looking at the destination Fibre Channel ID in the Fibre Channel frame. He's saying, okay, I'm not domain 1, but I see through my Fabric Shortest Path First routing table that I need to go out this interface to reach domain 1. Okay, so eventually that Fibre Channel frame is going to reach this edge switch. Okay, he's going to see that it's going to domain 1 and that he is domain 1. Okay, so he's going to look in this area field. He's going to say, okay, which area is which port is associated with this area so that I know where to egress this frame to. Okay? He doesn't really care what's in this field. He just knows that he has to forward out that specific area. So he's going to see that this port is actually associated with that area, so he's going to forward that Fibre Channel frame out that port, and it can get to that target. Okay? That is how we use Fibre Channel IDs along with Fabric Shortest Path First routing within a storage area network. Okay, does that make sense, guys? You guys tracking with that? Crickets. Okay. 1, it's usually going to be the principal switch. Okay? It's usually going to be the principal switch. Like I said, there's 2 different theories on this, though, and I have no way to prove it either way. Some books or some references say it's always going to be the principal switch maintains the Fibre Channel name server database and distributes it to the other switches. And then I've heard other theories that say all the switches listen to this well-known address of all F's and a C. Okay, so they all just build the Fibre Channel name server database by themselves. Okay, so you can go with either theory. What I really want you guys to know is, because that really doesn't matter too much, what I really want you guys to know is that the Fibre Channel name server database, every Fibre Channel forwarder has a copy of it. Okay, it's maintained by every switch in the network. Okay. So guys, this is the basics of Fibre Channel storage area networking. This is kind of the beginning of my Fibre Channel 101 spiel. Does each domain reside in a physical switch? Yeah, every fiber channel forwarder, every fiber channel switch will have a domain ID assigned, okay? So it's basically like a one-to-one basis. It's one domain ID per fabric, okay? We're going to start talking about virtual storage area networking here very shortly, okay? When we start talking about vSANs, we can have 4 or 5 fabrics within one switch, and each one of those fabrics is going to have its own unique principal switch and its own unique domain ID. Trying to ease you into the concept here. Okay? So this happens, guys. All right? This is a basic storage area network being built. We're going to introduce a couple different port types here in just a second. But before I get into vSANs and trunking, I want to explain this other type of F port, okay? Because this is the basic setup, guys. This is a regular storage area network. We can also have what we call FL ports or fabric loop ports, okay? So what you're going to see in our racks is that we have fabric loop. We have basically a JBOD, just a bunch of disks, okay? So one port goes to a shelf. Within that shelf, we have a bunch of disks within it, okay? So that's what we call an arbitrated loop within fiber channel networking. And just to help you guys ease into that concept, rather than connecting just to this maybe one disk or this one LUN, we're going to have a shelf of disks. So imagine a shelf, and maybe it has 4 or 5 disks in it. Okay, I'm going to draw a really big LC port so that you guys can understand this. So on top here, imagine that this is our plug for this shelf, and we have our kind of send pair and our receive pair. Okay. So this is just one fiber optic cable, guys. This is the send strand and this is the receive strand. So imagine that this connects to this shelf. What's going to happen is this arbitrated loop or this fiber channel loop, we're going to see the send come into one disk. It's going to loop to the other. It's going to loop to the other, loop to the other, and then exit out. Okay? So what we're going to see on a fabric loop port is a lot of targets off of one individual port. Okay? So we can have this designation of FL for situations like this where we have just a bunch of disks. All right. What you're going to see on the MDS switches is they default to a mode called FX. Okay. So an FX port can be either an F port or an FL port. Okay. So an FX port, which is the default on most MDS switches that are running newer software, when we plug that in, it can auto-negotiate. It can detect whether that's going to be an FL port or an F port, okay? So it allows us to go in there, and it's actually a pretty good default, right? Because you can hook it up, and it'll show us whether it's going to be operating as an FL or an F port. It's pretty cool. Zane, let me try to fix this up a little bit for you. Let me draw it a little bigger because that may have been too small. Imagine a JBOD or just a bunch of disks, okay? So a JBOD, okay? So we have this controller or this server that just has a bunch of disks in it. So imagine it has, again, 4 disks. So we have disk 1, we have disk 2, and I'll just draw 3. And we have disk 3, okay? Then on the top of it, or on the back, I'm just drawing, this is just a really big LC port, okay? And we have a send strand and a receive strand, right? Because when you have a fiber LC cable, one of the strands is going to be your send, one is going to be the receive, right? So what's going to happen on a fabric loop or an FL, okay, is that send's going to connect to the main board or whatever, and it's going to have a loop to disk 1 that goes to disk 2, that goes to disk 3, and then it's going to go back out, okay? So rather than just having like a one disk association or a one port name association to that one cable, we're going to have a lot of targets coming off of that one strand, okay? Does that make more sense? Yeah, it's just a bunch of disks. Just a bunch of zip. Well, EMC is going to operate more on what we call like LUNs or logical unit numbers. Okay, this is just a JBOD operating in an arbitrated loop kind of fashion. Okay, so to get from one end, so like when we actually ingress that port, we're going to loop through a bunch of different disks before we get to exit. Okay. Yeah, traditional SAN storaging like EMC is a little different, okay? With those guys, we're going to have all these shelves and these controllers and these shelves of disks in here. And we're actually going to go in and set these guys up in different RAID arrays. And we're going to carve out logical units from those RAID disks and present them to the storage area network, okay? This is a little different. This JBOD is what you're going to see in our labs today. So you'll be more familiar with it by the end of my demo. Okay? Okay, guys, we've had a lot to process so far. I want to go on to vSANs next. So let's take a 10-minute break. Okay? And when we get back, we'll start with vSANs. I'll finish up with some basic zoning talks, go in and do a demo for you guys. All right, so take 10 minutes and we'll come back and start from there. You can read and write with the JBOD.